Thank you. It's a real pleasure to be back here in Lund. I must confess to you that my later position in Berkeley, California originated directly from a research state here in Lund in 1982. So, no, I'm wrong. No, this was in, yes, 1982, absolutely, yeah. In 1983, I came to Berkeley. Yes, exactly. Lars Samuelson was the person who invited me. And actually, I'm always really grateful to be back here. I served for a couple of years in the advisory board of NanoLund, and therefore I was closely related to the very exciting research which is going on here, which is really globally leading research. But today, of course, I want to come to the topic which is closest to my heart, because my topic in 1982 was working on transition metals in silicon. And when I came to Berkeley in 1983, I noticed that the problems, the materials problems of semiconductor, of microelectronic industry with transition metals were as well problems of photovoltaics, of solar energy. And therefore, I, in my Berkeley time, could sometimes submit a proposal on the behavior of copper in silicon twice, you know, once to the Intels and Hewlett-Packards, and another one to Department of Energy to improve solar cells. So it turned out to be really a very, very fruitful time. But now let's talk about how to harvest nuclear fusion power from the sun, because all this, I shouldn't say nonsense, but this is a word which came immediately to the tip of my tongue. All this nonsense about pouring billions and billions in order to try to create a nuclear fusion reactor on Earth, in order to use the millions degree high plasma in order to drive a steam engine, 19th century technology, to produce electricity, is sheer nonsense in my view. It's nice and very exciting plasma research, but in order to talk about our energy supply, let's use nuclear fusion energy from the sun, because we have a much more elegant way to produce electricity out of it. And of course, this is using photovoltaics. And as a matter of fact, the development of photovoltaics and the renewable energy in the last couple of years is just enormously. You see that about 80% of all new investments in the energy field are now in renewable energies. You see here the blue bars, the renewables, and the gray bars, the fossil and nuclear industry. And you see today more than 80% of all newly installed power generation is renewable, because, you know, the idea that the upcoming climate catastrophe has to be addressed has really got hold. I don't have to mention Fridays for Future and so on, but I think these young people 100% are right, because if we continue to go where we are, the most likely effect will be that in 2050 we have converted the world energy system to renewables, because this is just economically the good thing to do, because the cost of electricity from solar and wind is the lowest cost energy you can have. But most likely we will do it too late, and we will have our climate spoiled with 500 ppm CO2 in the atmosphere. And then people in 2050 will say, how could you be so stupid in 2020 not to drop everything and to concentrate on the most rapid increase of renewable energy participation in the energy mix? And of course, you see, in the last years, there is even a special development that solar energy capacity even exceeded wind energy. But from my perspective, solar and wind are the two columns of the future energy system. So there is not really a competition between this. And what happened in solar since 1992 is almost unbelievable. This is a graph I extracted out of Wikipedia, and I dared to put a line onto this graph because it's a logarithmic picture. Since 1992, each year we added 37% of solar capacity worldwide. I don't know any technology which could consistently have such a growth rate over many, many decades. And still, I will hope to convince you that still today we are just at the beginning. And of course, in the last 10 years, the growth rate was a little bit low, but even 25%, I think, is an extremely impressive growth rate for any technology. This is a picture from the International Energy Agency from 2014. And I like to show this because when they produced this picture, it was already clear that we are just at the very, very beginning. But the difference to reality is they predicted at that time that we will end up with 5,000 gigawatts, which translates into 5 terawatts. But I will hope to convince you the goal is 50 to 70 terawatts. This is what we are facing when we want to convert the world energy system to a renewable-based energy system. And you see it already here at the beginning. We are already now far above this prediction, which at that time was considered to be a very bold and overly optimistic prediction. But this prediction, as so many predictions, is much too conservative. Today, we are very proud that in March of last year, we reached the 1 terawatt level. So worldwide, we have now 1 terawatt of photovoltaic energy generation capacity installed. The driving force for this fantastic development is, in principle, research, innovation, and at the end of the day, the cost of solar PV. And this is a PV learning curve since 1982, and you see that from 1976, when we had to pay $100 per watt peak for a solar module, today we pay about 20 cents for the watt peak. That means we have a consistent 13% annual price reduction. And if we go today, we can now make PV electricity at less than 2 cents per kilowatt hour in sun-rich areas. The lowest number I have seen was 1.1 cent in a public procurement in Portugal. So we are very rapidly approaching the 1 cent per kilowatt hour. And if we have electricity for 1 cent per kilowatt hour, this opens, of course, completely new technologies. So all this talk about the rising energy costs because of the transition to renewables is completely off the mark. Actually, as soon as we got rid of the CO2 emitting fossil energy, and if we get rid of the very expensive nuclear power, then we will have a future of very low electricity prices. And this is really what we should prepare for. Therefore, the development of green hydrogen and all power to X, to chemicals, makes all sense because we will have this very low cost. Let's have a look at technology, because there was a very interesting technology race between thin film photovoltaics and crystalline silicon photovoltaics. And you see back in the 1980s, this looked like a very increasing fraction. Even many people in the field, colleagues of mine, said thin film is the second generation, crystalline silicon is the first generation, and why should we cover our roofs with the wrong technology? Let's wait for the thin film technology to come. This was a statement from Steve Chu, who was at that time later he was the Energy Secretary of the United States, Nobel Prize winner of physics, but this was all wrong. Today we have 95% crystalline silicon technology. And let's have a look a little bit about the technology. The standard technology till about, I would say 10, 12 years ago is shown here. It's called aluminum backsurface field. You have a P-type wafer, you have an aluminum backside contact, you make, of course, the anti-reflection coating, you make the screen-printed contacts, and finished is the old industry standard technology, which has a limit of about 20% of efficiency, which 20 years ago was a good number. Today, of course, we are not longer satisfied. We want to do better, and the main problem of this technology was the aerial contact between aluminum and silicon, because any contact between metal and silicon is as well a recombination site. So PERC technology solved this problem by covering the backside with a passivating layer like SiO2 or Al2O3, sapphire. But you need, of course, to contact the material, and in PERC the solution was to use a laser, With a laser, you can set 1,000 points in 1 second, because you know the laser is being controlled by computer, and you can do this in 1 second. And then you only have individual points of contact between metal and the silicon. 99% of the surface is well passivated, and this PERC technology is now the world dominant solar technology, and the glass ceiling of this technology is about 24%. It's already 20% more than the ALBSF technology, and the most interesting factor for the big Chinese manufacturers of this technology was you can convert a standard ALBSF technology line, a production line, to PERC. You just have to exchange a few machines. Now, today, as I speak, we are in the transition to the third generation of crystalline silicon PV technology. And there we have mainly two choices, the TOPCon technology and the heterojunction technology. In TOPCon, it's a continuation of the PERC technology, which I think for physicists is very interesting. Simply go away from these contact points by making the passivating layer so thin that carrier tunneling can make the contacting. So preparing the whole backside of the wafer as a tunnel oxide contact, and then of course you can get rid of the laser produced metal points, and therefore TOPCon technology allows to go up to about 26% as it is here. The alternative is heterojunction. Heterojunction technology, completely different approach. You cover both sides of the wafer with amorphous silicon. On one side, P-type amorphous silicon, on the other side, N-type amorphous silicon. And then you have amorphous silicon in contact with crystalline silicon, which doesn't, it's a perfect passivation for the silicon because it's only silicon-silicon bonds. But in addition, today we know how to dope amorphous silicon, so you can as well use this amorphous silicon as a good contact to the silicon. So heterojunction technology is an alternative to TOPCon. TOPCon technology is a technology which is most interesting for the owners of huge gigawatt scale production lines, because they could convert from ALBSF to PERC and then to TOPCon. It's the same technology, you just change the equipment for the tunneling contact. Heterojunction technology is only used for people who come new into the field. And I think for us here in Europe, it's a very exciting technology because we are not head-on with 300 gigawatt of production capacity of the existing PERC lines, which are in China. So this is where we are today. But of course, we don't want to stop at 26%. What will happen beyond? Beyond 26%, we have to really deal with the absolute ceiling of silicon technology, the so-called Shockley-Queisser limit of about 29%. And how do we do it? We have to make tandem cells. Tandem cells where a good silicon solar cell on the bottom can provide the first 25% of efficiency, but we add a top cell which has a wider band gap so that the light for the silicon cell still is transparent, but you can create additional carriers with a higher band gap, and therefore you can shift the efficiency beyond the Shockley-Queisser limit. Whether 3.5 top cells, where we would have to develop low-cost 3.5 deposition technology, or whether perovskite top cells, or maybe even 2.6 top cells will at the end of the day be the winning technology, we don't know yet. But in any case, we can say very exciting technology developments are still going on in silicon cell technology. It is absolutely sheer nonsense to call silicon solar cell production a commodity production. You hear this a lot from politicians and others, but it is nonsense. Silicon solar cell production is a semiconductor production. That means the production line of DRAMs and other microelectronic circuits. You deal with silicon wafers, and actually quite a few innovations in the microelectronics field came originally from the photovoltaics range. For instance, the multi-wire saw, because the microelectronics people could cut one wafer after another technology. So today everybody uses this technology which came out of solar. So let's really agree on one thing. Solar cell production is high-tech, has still a lot of innovative potential, and therefore it is, of course, for Europe. I convened terawatt scale. Here on the right-hand side, you see, for instance, Martin Green, the solar pioneer from Australia, and maybe some of you who are familiar in the solar scene can recognize quite a few people. And there we made a couple of scenarios where and how could solar develop. And we agreed that we will reach the terawatt scale very, very quickly. As I said before, just now we have 1 terawatt installed, but here we talk about here we talk about total capacity, and we expect that we already come into the terawatt range, in the multi-terawatt range by 2030. Whether these are 4 terawatt or 10 terawatt, we could not decide at that time. Today, we can say our most optimistic scenario is exactly where this first terawatt, which was installed in March 2022, is. So that means this upper line, which comes by 2030 already above 10 terawatt installed power. This seems to be the line which the world is following. 3 years later, we had another workshop. This was published in 2019, where we again said these are the possible scenarios of the cumulative PV capacity. And there we say 2050, we will be in the range 60 to 80 terawatts. And as a matter of fact, the latest workshop, which we just had last year, which we published in April of this year, shows that we expect to come to about 75 terawatt by 2050. 75,000 gigawatts installed, and today we have 1 gigawatt installed. It means we are just today at the very beginning of this technology, not at the saturation level. And you see on this graph, we are now producing about 300 gigawatts of PV. We expect this to come at least to something like 3 terawatts by 2035 or so. 2030, we should cross 1 terawatt annual production. So what we produced in the last 30 years, the first terawatt, we want to produce in 7 years from now per year. This is really the revolutioning development of PV, of the PV industry. And yes, this was exactly what I wanted to say. But now comes a very important point, and this is the question, where is this produced? And please, this is the solar cell production. If I would make a similar graph about solar module production, the picture would be much broader. In Europe, we have about 10 to 15% of the worldwide solar module production. But making a module means simply to put the silicon solar cells together, encapsulated frame, and the module production is a very low-tech piece of work. But the solar cells are the heart of all modules. The solar cells are where the sunlight is converted to electricity. And there we have a completely untenable position. Only 0.4% of the global solar cell production is in Europe. 0.3% is in the United States. So you can hardly see this on this graph. You know, here, Europe and the United States were at least visible, but today they basically disappear. Vietnam alone produces 1.1% of the global solar cells. So Vietnam has a larger solar cell production capacity than Europe and the United States together. I think this is, when one thinks about geopolitics and what can happen with countries who have an authoritarian leadership, this is a completely untenable position, and I hope sometimes the politicians wake up to this challenge. So let me summarize. I think we completely agree that PV will be a key or the key pillar of our future energy system because it is the lowest cost way to produce electricity. We expect to reach 1 terawatt per year annual production by 2030, and maybe 2035 we have 3 terawatt per year, which is 10 times what we have today. And we will grow to about 3 to 5 terawatt by the end of this decade, because we need to go to 70 or so terawatt to have the whole world energy system converted to renewables. Silicon wafer-based technology are the key of solar technology. Of course, we go from PERC to TOPCon or heterojunction, and then to tandem structures where we can exceed the 30% efficiency limit. So many exciting innovations are still to come. The absolute world record of solar efficiency is 46% with a multi-level 3-5 solar cell, which is very good for applications in space, where cost is not so important as the efficiency, or in concentrated solar cells on Earth. But at the moment, they are more expensive than using standard silicon-based technology. And of course, all these innovations and the latest developments are built on novel material systems and on nanostructures, such as the ultra-thin oxide tunnel TOPCon barriers. Actually, this TOPCon technology still is a very challenging technology, because imagine you have to cover a 200 millimeter wafer with a 1 nanometer, not 10 nanometer, 1 nanometer thin tunnel oxide. It's easy to demonstrate this on a 2x2 cell, square centimeter cell with atomic layer deposition and so on, but we have to do it high throughput, lowest production cost, so there is still some technology challenge ahead. But the big Chinese PV companies, they of course wait about for TOPCon, because then they can convert their gigantic production lines easily from PERC to TOPCon. For us in Europe, I personally think that the amorphous silicon, crystalline silicon, amorphous silicon heterostructures are really at the moment the possible entrance door to be a world leader in PV manufacturing of this new third generation technology. This is our chance and our opportunity, and later then we can continue to go on to the novel tandem structures which I described. So I want to summarize. I think solar energy harvesting will be as interesting, as much economic activity as today's oil and gas and automotive industry. As a matter of fact, if you take the 3 terawatt number annual production series, this translates to more than 1,000 billion US dollars or euro annual market. And the automotive market worldwide is 800 billion euros. So it will be the same market size as the world automotive market in just the solar cell, solar module market. This is a thinking which most people have not yet entered, and I think this is where what we should think about. And my message is, we still have a technology chance. We should not simply say, oh, the Chinese do it and they do it for low cost. We still have a technology chance in the third generation technologies and later in the tandem technologies to be world leading, not just because we want to be autark. We should never say we want to be autark, but we want to be technology leaders, and we want, of course, to use what we have invested in our research and development in the last decades in Europe, and we have done this very successfully, but we want to have as well the industry and the jobs here. So this is the opportunity which we have, and this window of opportunity is not more than 2 years, maybe even less. We have to act now, and thank you so much for your attention.
Thank you so much, Eicke, for a lot of sympathetic provocations here. You used the word nonsense quite a lot. Also, nice.
You know, I am a retired professor, so nobody can cut my salary or do bad things for me.
No, it's good. And what I really liked is that you gave us a very positive outlook of the possibilities.
Yes.
Even with a 26% efficiency, which I find miserable, but okay. We have already a lot of questions. Yes, please. And also, you have the chance, if you're connected via your computer, you have the chance to bring some questions, and we'll try to bring them up here. Please, I'll come up with a microphone.
Hi, my name is Anja Hase from EuroNanoForum. Thank you for this very interesting talk, and you also had it in your summary. You showed this impressive graph where Europe and the States is not visible,
Not visible.
anymore.
Yeah.
Are there any activities already? Because you said we have 2 years' time.
Yeah.
Is there already some?
Oh, yeah.
Okay.
Lots of things
So
are
do we
going
have a
on.
chance?
Yes. Thank you. That's actually a Steilvorlage, we would say in Germany. You know, in Europe, we have already the development, and I am co-chairing the European Solar Manufacturing Council. There are about 5 gigawatt scale projects underway. Most well-known is from Meyer-Burger in Germany and from Enel in Sicily, in Italy. But there are others, and I am personally as well trying to push a startup company, MCPV, in this field. Together we are under an umbrella called European Solar Initiative. So this is being coordinated. And of course, the big challenge is the United States. The United States was so bold to put through the US IRA, the Inflation Reduction Act, where not only they put in lots of capital expense support, but as well a very powerful operational expense support. And it is so crazy that we in Europe don't want to copy this. The idea of this is the following. We take the tax income from the new company producing solar cells, and we pay out of this rebate corresponding to 30% of the production cost of the solar cells. So that means it's a subsidy to bring down the production cost by 30%, but this is not paid out of the state budget or the European budget. It is paid from the tax income of the companies, which wouldn't exist if there would be no PV production. So it's such a no-brainer that I don't understand. I always hear...
I can interrupt you.
Yeah, it doesn't go with European
law. The
law.
non-brainer is that we need to see what the internal market is doing for Europe, and that we need to create and keep a level playing field, and that not the one member state with the deepest pockets.
But we don't have
We are not the United States, and we have done, also this is for the window of opportunity, with the Net Zero Industry Act, where solar panels are one of the 6 products we want to bring back with very ambitious targets. We have a very interesting, also financially interesting package to support production in Europe for exactly the reasons.
But this supports only the CapEx, the investment in the equipment, and investors don't give you money in a company where they cannot have a guarantee that you will as well sell these modules.
But if we go into operational costs, the disruption of the internal market, the level playing field is much deeper.
Yeah.
We need a beer and a dinner for that.
Yes.
Eicke, thanks so much for your passion. We have more questions here. Please.
Thanks a lot. It's an inspiring talk. I'm not retired professor yet, but my name is Professor Fahmy from Rhine-Waal Applied Science University. We have always, when I'm teaching this, I always facing, if we have high temperature, the efficiency of photovoltaic getting down around 15%. And that's a significant part of the efficiency. Do you
What do you mean? You mean degradation, or what?
No, the efficient. If you have, for example, 9 o'clock in the morning, you have a nice efficient. If it's getting hot, 12 o'clock or 1 o'clock, you face, I have this in my roof, in my house.
Yeah.
You face getting down despite the sun is quite very, very effective in. I can recognize 15% getting down.
Yeah, I mean, you know, what counts at the end of the day is how many kilowatt hours can you harvest out of a kilowatt installed, and this is a fixed number. Of course, the distribution over the time of day is absolutely like you described, but at the end of the day in Germany, we harvest about 1,000 to 1,200 kilowatt hours per kilowatt installed, and if you put the same solar panel to Algeria, you will have 2,000 or 2,500, you know. So these are the numbers, and of course, distributed over time, you're absolutely right that when it's getting hot, the efficiency goes down. By the way, this is very good for the concept of floating PV, where the solar modules float on a water surface, which prevents evaporation of water and keeps the module cool. So there you will have a constant efficiency.
There's time for one more question here.
Okay.
Yes, we hear you.
Can you hear me?
Yes.
Okay, my name is Lina Killander. I come from Vinnova, the Swedish innovation agency. And I have a question related to critical raw materials. Is that
Yes.
a cloud on your sky or no problem at
Oh,
all?
absolutely. Thank you so much for this question, because this is really one important point. In order to have PV industry, you need the full wafer chain. It starts with actually, it starts with polycrystalline silicon. You have to grow a single crystal, you have to pull the single crystal, you have to cut it into wafers, and then you have the wafers for solar energy. Luckily, we still do have these initial stages in Europe. Wacker is one of the biggest polysilicon producers. In Norwegian crystals and Norsun, we have wafer producers. So these are not yet set up to supply the intended. We want to have 30 gigawatt of PV production capacity in Europe in a couple of years, but they say they are ready to scale up as soon as the market is there. And then the second answer to this question is, we do have in our sleeve a new technology which was actually developed in Fraunhofer ISE when I was director. It's called Next Wave, where we don't grow single crystals. We use a seed wafer of silicon. We treat it electrochemical to make it porous, and then we use thin film deposition to deposit our wafer. And then when we make a thermal shock, it pops off, and we have the wafer without losing half of the silicon material in the cutting process. This technology is not yet in the market. It's TRL level 7 or something like that. But this is another solution to this issue.
Thank you. Thank you all for your great question, and thanks, Eicke, for great answers as well.
My pleasure.